Welcome, dear students, to again another lesson 3 of electrochemical reactions. So I hope you're following this series properly, and today we're going to talk about the extraction of aluminium. So we want that metal at the end of the lesson. We want to have extracted it from its mineral ore. So you may wonder why I want this aluminium. Remember, these are electrolytic cells. We're using our electricity here, our energy, so we must have a good reason for doing it. So please just notice that aluminium itself is actually an excellent electrical conductor. It is malleable, which means it can be rolled into thin foils, and it has a high tensile strength. Those kind of things you must know. Well, it's low density as well. It's an advantage to it. That is why aluminium is considered to be a precious. It's actually those metals that we may want to extract right now. So now definitely we're talking about a less dense and hard, metal that we've got here, aluminium. So it's one thing to have such a metal. It is less dense and yet it is quite strong. So even on electroplane bodies, they use this aluminium, even on cars. So you see, it's quite a metal that we need. All right, so let's go ahead and start talking about extracting it. You see, everything, if it's a mineral, we are going to dig it from underground. And if you're digging something from underground, it's going to have impurities. Well, sand being one of those. So it's silicon, it's a silicon dioxide. And also we have iron. Those are some of the impurities that will be there. So to get those impurities out, we will have to actually wash it. So the mineral ore that you get from underground is called bauxite. This one. So this is what you get from underground. So it's the raw material that we need for this electrochemical cell that we're going to talk about. So that bauxite that you get from underground, like I said, you're going to wash it or rinse it in sodium hydroxide. You actually do form aluminium hydroxide, but that aluminium hydroxide is going to quickly be heated to produce what is called alumina. Well, that is just aluminium oxide. So at this point, you have pure aluminium oxide. So what it means is that you almost have your aluminium now. Such impurities, those silicon dioxide and iron and all that, when they were rinsed here, the waste product is an alkaline suspension of iron 3 oxide, which is actually called red mud. It's pumped into red mud dams, and we let it go here. So now we have our pure aluminium oxide. Well, we were going to go ahead and just perform electrolysis on this aluminium oxide, separate our aluminium from the oxygen using the process of electrolysis, and things were going to work. But the main problem is it has to be a liquid first. You see, you have to try and make aluminium oxide a liquid first, and that is the main problem. Because if you try to make it a liquid, it will only melt at about 2045 degrees. To 2050 degrees Celsius. That's a very high temperature. Very hot water is only 100 degrees Celsius. So then if you're thinking of 2045, just think of how high that temperature is. It's in degrees Celsius. So this requires quite a lot of electricity, a lot of power that is used here to try and melt aluminium. At the end of the day, it will not be worth it at all to do this thing, to extract aluminium. So scientists don't run out of ideas. So there is a method that we use now. Instead of just making sure that aluminium oxide becomes a liquid by melting it, we are not going to go to this ridiculous 2050 degrees Celsius. Rather, we are going to dissolve it in what we call molten cryolite. So the formula is just this one. It's some sodium aluminium hexafluoride, this one right here. So when you dissolve it in molten cryolite, the aluminium oxide, you put it into that, well, it reduces its melting point, the working temperature. It reduces it to something about 900 to 1,000 degrees Celsius. So it's still high, people. It's still high, but at least it's not as high as 2045. If we are working at 900 to 1,000 degrees Celsius, we've managed to halve the temperature that we had at first. So that's the best scientists have done so far, to melt our aluminium oxide, which we call alumina here. So we melt it in actual fact, we dissolve it in sodium aluminium hexafluoride, and that will lower its melting point to about 900 to 1,000 degrees Celsius. So please, when we do that, you can tell that there is an economic advantage to it. We are saving energy at this point. So that is the main reason. Please, whenever you're asked, why do you dissolve aluminium oxide in sodium aluminium hexafluoride or in molten cryolite, you should know that it is to lower the melting point of alumina. So please, that is important. Get that theory in your head. Well, now, after we melt it, now it's in liquid form, right? The aluminium oxide. Well, now we can take it and do electrolysis with it. So we can make it our electrolyte, actually. And when we make it our electrolyte, if we choose some electrodes, some inert electrodes, such as maybe if we are going to actually use carbon ones, the graphite ones this time, if we use those ones, then we can actually let aluminium oxide undergo electrolysis. Remember, I said it was the decomposing of a compound by passing an electrical current through it. So the aluminium oxide is going to be dissociated to its own ions just now. So let's watch as we do that in the next cell. Well, you may look at this one. Please notice this was a scientist who thought of this type of cell, the setup of the electrolytic tank. It was Hall Herold. So Hall Herold cell is really like this. You might be wondering what's going on here. It looks like a house. Well, if you think of it that way, then perfect. It's fine that way, because we're going to call this one the roof of the house, the top part. Notice this part here. If it's getting darker, it means I'm highlighting it. Well, it's interesting to highlight in black, but here we are. So please, that right there is our anode. As you can see, it is positively charged here. You see these anodes of ours, they're positively charged. So can you see they're connected to the power supply? So this is the positive side of the power supply, the positive terminal. Well, so this whole part here, like I've already indicated, it is positively charged. This is the anode, all of it like here. So I always say it's a tank with a roof that is positively charged. These ones are anodes right here, anodes. And you know what? These anodes are made up of carbon. These are carbon electrodes. It's written over here. So it's carbon in form of graphite. Okay? So this is graphite that we are dealing with here. That is what is at the anode. So what then is at the cathode, you may wonder? Well, the cathode, as you can see, it's connected to the negative terminal of the battery. So this, I was calling this part the roof, right? So this one right here is at the walls of this tank. The walls of this tank are actually still made up of graphite, and they are negatively charged, as you can see. So this is still graphite, hey people. The walls itself is graphite. What is labeled iron there, this part is the inner part, this part where you can see this one's moving around. But the wall itself is made up of graphite, still a form of carbon. All right. So now what have we done so far? We have charged the top part as the anodes, positively charged, and the walls of this tank are negatively charged, which means they are the cathode in this. All right. Now what happens? We are going to pour our alumina, if you still remember, in molten cryolite. You still remember that liquid, right? Well, as you can see, that liquid is the one that is here now. So it's over here. All right. So like I was saying just a few minutes ago, this liquid right here is our aluminium oxide. Well, it's together with sodium aluminium hexafluoride, the cryolite. So that's the liquid that you're going to put here. Well, from what I just said, electrolysis is going to take place. And from what we know, electrolysis, when it takes place, it dissociates. Let's do this. Let's take our aluminium. Let's take it right here. Okay. O3. And I hope you still remember how we do this, how we get this compound. Aluminium is in group 3, so it will form something of this sort. And oxygen is in group 6, and you know that it forms that. So from what we learned back then, we said the 3 will go to the oxygen, and the 2 comes to aluminium. So that's how we know that aluminium oxide should look like this, right? So I hope you still remember how we were doing these compounds back then. Just thought I should remind you. Okay, not to worry about that. Now, aluminium oxide now, like I'm saying, it's going to dissociate to its own ions because of the process of electrolysis. When the power is switched on, the first thing that aluminium will do is to go to its ion, aluminium 3+. It's in group 3, this aluminium, so it's 2 of them, just to try and balance it already. And then it's going to be 3 of the oxygen, which is in group 6, so it gains 2 electrons at this whenever it is in ionic form, according to what we know. So this right here is what is going to take place. So these ions are responsible for conducting electricity, as we already know. Well, they are in here as well. So we do have aluminium 3+, as you can see, some O2-, and then now you're wondering, where do they go? How does it work? How do we eventually get our aluminium? Because remember, what we want is to get aluminium afterwards. So how does it work? Well, like I said before, the opposite charges will attract. Don't forget that the cathode is negatively charged, right? And our aluminium is floating and it's positive right there. So it's going to be very simple for us to determine what happens at the cathode half reaction. So the aluminium is going to go to the walls of this tank, and it is going to get 3 electrons from there to become aluminium. I was going to say aluminium solid, as I usually say. When we're talking about these electrolytic cells, I would say that aluminium gets, or at the cathode, these metals get adhered to the cathode. A layer of that thing is formed at the cathode. So you're most probably expecting aluminium to form a layer on the walls like this, but it's not going to happen this time around, because aluminium itself is actually a liquid at this temperature, because we are working at, if you remember, we are working at between 900 and 1000 degrees Celsius, and aluminium's melting point is 660 degrees Celsius, around there. So if at that point aluminium is not going to be able, let me just show you what I'm trying to say here. From what we know, aluminium should move from let's have this aluminium. It should be able to go to the cathode, right? And then when it goes there, under normal circumstances, it should be a solid here. But because of the temperatures we are working in, it is actually in liquid form. So it's like putting butter on a very hot knife. It is going to just slide down. So aluminium, you will see that it will try to adhere to the wall, but it will just slide down. And as you can see, it's the one that we have formed here on this black part. So molten aluminium is going to go at the bottom. When it settles at the bottom, it will be tapped out through this point here. And as you can see, this is the part where we get the molten aluminium. It's a good thing we're getting it in liquid form. It means we can really shape it into whatever form we want while it is still in liquid form. So please, people, this is the cathode half reaction. Well, now that we know the cathode half reaction, let's talk about what exactly happens at the anode. We know this is the reaction taking place at the walls. So what happens at the cathode, at the anode rather? Well, as you can see, at the anode, we are expecting for oxidation to take place. Well, this is something I would like for you to see a little bit later, so let's hide it a bit. Okay, so now what happens at the anode? Well, the oxygen, this one now, so the oxygen, which is O2 minus, should definitely, you know that oxidation is what takes place at the anode, right? And oxidation is loss of electrons. So that one is going to lose its electrons. Let's let it lose everything, and then it is going to give us 2 electrons. Very weird, isn't it? Isn't it looking weird right there? Well, I always do that just so you can remember that your oxygen has to be a diatomic. So you need 2 of them here. And of course, at that point, you can see that if each one is giving us 2 electrons, if there are 2, they will give us 4 electrons. So this is the anode half reaction. This is what is supposed to be taking place at the anode. Like I've already indicated, the anion will be attracted to the anode. So that is precisely what we are saying, that the oxygen will go to the anode. But you see, again, another thing is taking place. You know, we will form a gas. There will be a gas that will be seen on these electrodes. There will be bubbles of gases at the anode. But that gas that goes out is not exactly oxygen. Fun story, right? So which gas is it? Unfortunately for us, our anode is made up of carbon. So the carbon is actually going to react with this oxygen to form carbon dioxide, like this. So how does that work? Well, like I said, we are working at 900 to 1000 degrees Celsius. So even the very unreactive carbon, remember that the anodes are made up of graphite. Well, they will react with the oxygen that we formed here, and they form carbon dioxide. So the gas that we will see, the bubbles of gas that we'll see up here, are not the bubbles of oxygen as we were expecting. It will be bubbles of carbon dioxide, unfortunately. So this is the reaction that then happens, or that is responsible for something else, as we will notice. Now, let me explain that. This carbon, like you know, is actually what the anodes are made up of. So in other words, the anodes are burning up. This is a combustion reaction. Your carbon, which the anodes are made up of, is being burnt. It's reacting with oxygen. So it's like they will be, let me use the word corroded. They will be corroded with time. They get used up as they are reacting, the anodes. And you know what? The carbon dioxide is escaping into the atmosphere. So all the time we get 1 more of carbon dioxide, we would have lost 1 more of carbon graphite, which are our anodes. So from time to time, we have to replace these anodes as they are getting burned up in the process. So that again makes this process quite expensive, because firstly, you have to put a temperature of 900 to 1000, and again, you need to replace these anodes occasionally. So again, you see, that's why it's expensive to actually extract aluminium, as we are noticing. So your notes are here already. So let me show you what I was hiding from you. This part, it's very important that you keep it with you. So the reaction that I said is responsible. Notice it. Carbon reacting with oxygen to give you carbon dioxide. So it will escape into the atmosphere, and this is precisely what I was saying. The reaction will lead to regular replacement of carbon electrodes as they get used up. So hence the high operational costs. So I think at this point, you now know what happens at the anode and you know what happens at the cathode. So let's just write what we call a net reaction in this situation. Let me see if we can use a new page or this one. Okay, let's rather stick to this page for now. Okay, so I'm saying if you want the net reaction, you write what happens at the anode. Well, if you still remember the anode half reaction is that one that forms oxygen. That's the anode half reaction. So let's copy it down. We said it was 2 of that. 2 oxygen atoms. not atoms, ions, giving us just oxygen plus 4 electrons, like that. Well, this is the anode half reaction, right? Then you copy down the cathode half reaction, which is over here to your left. So I'm going to write that one down as well. So it's aluminium 3 plus 3 electrons is going to give us aluminium. Well, here we are going to dance around a bit because the electrons are not balancing. Look at these 3 electrons that are here and 4 electrons over there. We are not going to just write what's happening on the left-hand side and what's happening on the right-hand side. We're going to have to get the LCD of 3 and 4. In this situation, let's use 12. So to get to 12, you have to multiply the first equation by 3 and multiply this one by 4. So let's rewrite those reactions after that has happened. So now the new anode reaction will be 6 of the O2 minus, and it's going to give us 3 of the oxygen plus 12 of those electrons. Well, this one, if you multiply it by 4, well, 4Al3 plus, it is now 12 electrons as well, and it is going to give us 4 aluminium as well. Well, I am now going to write the net reaction, and it may appear innocent to write it like this. Look, I'll start with 4 aluminium for this one for now, and then I'll write that one later. You see these electrons are cancelling out fine, right? So it's aluminium 3 plus, and then plus 6 O2 minus, giving us 4 aluminium plus 3 oxygens. Well, at this point, it looks rather fine to do so. And remember, this one, we're getting it in liquid form, and that's a gas. But here on the left-hand side, we do not want to leave it like this, okay? We don't want to leave it like that. We would like to try and really write the compound itself. So you know that aluminium 3 plus and oxygen 2 minus like that will form aluminium oxide. So firstly, write aluminium oxide using these charges. Just reverse them. So you need to put aluminium like this with a 2. Aluminium is the one that will get a 2. Oxygen is the one that will get a 3, right? So I use these numbers wisely as we have indicated. Now you need to look at these numbers here. You need to eventually have 4 aluminium. So to have 4 aluminium here, you may need to put a 2. Now, eventually you need to have 6 oxygen. So you have to see if when you multiply 6 and 3, if you're getting 6. If that happens, it means you have the correct compound. So I prefer you use this one because that's what we started with. It is actually in liquid form, and then we get our aluminium. This side you can leave it as it is. So this will be the reaction that is really taking place. We are starting with aluminium oxide when we start this reaction, which is our alumina here, and then eventually we are going to get our aluminium. We tap it out through this opening here on the diagram right here, and then the oxygen, unfortunately, it's going to react with the carbon electrodes on its way out. So it will be, we won't be able to get our oxygen, rather we get carbon dioxide, which is going to cause a bit of global warming, as we will notice after some time. So that is what happens there. Okay, so I think you now know everything you required to know about this reaction. If you can get to this point and understand everything, then you're good about the whole Anode cell. Well, there are environmental impacts, you see. We have a risk to the environment on this thing here, so you need to be able to know all of that. So you already have it. I put some on your notes over there, so keep that in mind. So you know that we have energy problems associated with the whole Anode cells and even the environmental problems. So on the energy part, please notice that we work at very high temperatures, and hence we will need a lot of electrical energy to do that. So at one point it is actually reasonable mostly to recycle it rather than manufacturing it from scratch, since recycling it will only need 5% of the energy. Please think about it. 1 mole of electrons will only produce 9 grams of aluminium. So 1 mole is quite a big charge right there. So it's very unfortunate, but this aluminium plant, an aluminium plant only has to be put up if there is a nearer electrical source, or if it is cheaper to have electricity at a certain place. Other than that, it won't be reasonable to have an aluminium plant. They won't approve it because of the high energy requirements. Well, we talked about carbon dioxide, right, being formed. The reaction is still over here. Well, notice that carbon dioxide will contribute to the greenhouse effect, which we normally call global warming. So we don't want the climate to change. So unfortunately, these gases are not very good to the ozone layer at all. Well, you know that the molten cryolite that we talked about, unfortunately, it has fluorine, right? So the fluorine that we were talking about, it actually forms some products that are actually harmful to human beings themselves. So they are poisonous to human beings. We would like to, it's again a risk that is involved in this electrolytic cell. We talked about the red mud sludge. We say that after rinsing our ore, our bauxite, we actually just have that alkali that we dump into red mud dams. Well, the red mud dams are alkaline, and this is alkaline, so it will contaminate groundwater most of the times. So we don't want that one as well. Carbon monoxide, well, if we don't have enough oxygen to get to carbon dioxide, there will be carbon monoxide that is formed, which is already poisonous. Sound pollution being one of those ones that you want to think about as well. Just know a few things about this. It's very easy to remember this type of thing. Well, let's have an examination type question on this before we go. Well, here it is. We have an aluminium oxide in an ionic compound. It is found in the Earth's crust, is known as bauxite. Well, we are seeing that. Well, we know it contains aluminium oxide, and we are going to pass electrical current through it, as we are noticing here. Do you still remember what we said? The anode, it is connected to the positive terminal, right? So this is the anode right here. This whole thing, even up to there, is still positively charged. And I also said that the walls are the ones that are negatively charged. Both of them are made of graphite. Graphite, which is a form of carbon, okay? Carbon in form of graphite. It has delocalized the electrons, this one. So therefore, it's a nonmetal that can conduct electricity. Well, we know very well that this one right here is molten cryolite together with our aluminium oxide. So we will have a bit of aluminium 3+ in here, and we have O2- in here, a lot of aluminium 3+. You know, that is what will be in here, okay? So that is what you have to remember. At this point, I think you still remember it. What I'm asking you is to continue to remember it until you write your exams. Well, let's figure out what questions were asked in here. The first thing is define the term electrolytic cell. This one, I think at this point we know. It is a cell in which electrical energy is converted Okay, so it's converted to what? What do we convert electrical energy to? Right? It is chemical energy. Okay, I hope we could wait for all of that. Okay, so that is actually an electrolytic cell. What is cryolite? Why is cryolite added? Why is cryolite added to the bauxite before it is melted? Well, it lowers the melting point. So let's go. It reduces the working temperature from 2050 to about 900 to 950. So we are going to say it lowers the melting point. We know now that if you add some impurities to something, you may lower their melting point, or you may alter the melting point in some way. Okay, So it lowers the melting point of aluminium oxide or the bauxite. Okay? Yes. So that is what you must remember. Give the symbol of the ions present in the molten aluminium oxide. Give the symbol of the ions present in the molten aluminium oxide. Well, I doubt this is too difficult to see. So there will be aluminium 3+, right? And also oxygen 2-. We talked about that, so I think it should be easy to understand. Write down the half reaction that takes place at the cathode. At the walls, what's happening? Well, aluminium is being reduced, so it gains 3 electrons, and we get to our aluminium. And this time, it will be in liquid form. Okay, so this is the half reaction that takes place there. Explain why the carbon anode should be replaced regularly. Make use of a chemical reaction. Well, I'm not going to write the whole statement down, but do know that the oxygen that forms at the anode reacts with the carbon and forms carbon dioxide. Therefore, the carbon is oxidized and must be replaced regularly. So please keep that in mind. I said the anodes, they react with the oxygen that is formed and they form the carbon dioxide. So therefore they have to be replaced regularly, isn't it? Because they are burning up here. They are reacting with the oxygen being formed. So I hope this helped you a bit to understand your whole Anode cell, and thank you very much for watching this one. Let's see what else we have in the future.